Everyone. So welcome to our second Pinnacle live stream cast for geometric application of calculus, and we are going. Hold on one sec. Okay, sorry about that. I felt I was talking to myself. Okay, so welcome to the live stream cast, and today's topic we're gonna talk about maximization and minimization problems. And I find that these problems tend to be quite tricky for a lot of students, and they tend to be in the hardest part of the exam paper, mainly in the 2-unit paper. But for your upcoming assessments, most likely it can appear in both the extension paper and the advanced paper. So we'll take a look at some of the very common type of exam questions in this area, and hopefully you can learn a few things from these examples. All right, so if this is your first live stream, welcome. If you attended the last live stream from last week, you probably had a taste of the format. We are continuously improving the format. I mean, this is all very new to us, and we are still trying to determine what is the best way to deliver these high quality content to everybody. Now, if you did miss out on last week's live stream, feel free to go to our website. So I'll show you in one sec where you can find that. And it's on curve sketching. Feel free to go and review that whenever you have time. So in terms of the format for today, I think after experience what happened last week, the best way to go forward is we will have a 1 to 1.5 hour presentation on the topic. So today will be on maximization and minimization. I think the length is variable really depending on how difficult the subject is. I have a feeling today we might be stretching it to about 1.5 hours. I do like to interact with my students, so feel free to join our Facebook group. I think instead of doing a live Q&A, we'll just host it as a discussion group. So I'll show you where all that is in one sec. Now, during the live stream, you can absolutely interact with us, and we encourage you and interact with us, because I feel like sometimes I'm just talking to a computer. It's very hard for me to gauge, am I going too fast? Am I going too slowly? Did I not explain something in the amount of detail that you need? So I'll show you where you can interact with us as well. And please leave us a feedback on the discussion group, or even just email us. That will greatly appreciate it. It just really helps us improve the delivery and continue to do this for the future students. All right, so I'm going to show you where all of these things are, just going back to this. All right. So if you go to the YouTube's page for this live stream, you can see there is a chat box over here. So feel free to say hi. Okay, so ask your questions. So feel free to interact with here. I will be checking that and monitoring that. So if you have any questions at all, or you feel that I'm going too quickly, that's where you can talk to us. Now, in terms of resources, so just going to our website here. So our website is www.pinnaclecoaching.com.au. To get to this page, just go to resources, Pinnacle Live Online Lessons. So from here, if you click on the first link, that will take you straight to last week's live stream, and you can see all of that material. There is a practice set there as well. I think it just makes great revision resources. But today, you can click onto here, which will also take you straight to the YouTube live stream here. And there are resources you can download here. So there's a student booklet, which is basically the examples we'll be going through today in this live stream. You can follow through, follow that with the student book. It's basically got all the questions there, and you can write down your answers right there. And if you're up for it, definitely try the practice set. This is like a practice that I've curated for very short but intense type of practice, so very relevant. And I think there's only like 6-7 questions for this topic in that practice set, but that gives you a very good sort of litmus test as to where your abilities are, and they are all exam style questions, so you can see how is this area examined and where your abilities are. It's got fully worked solutions, so make sure you help yourself to it. And in terms of the discussion group, so here it is. So you just type in Pinnacle Live discussion group. Happy to answer any question here. I thought Facebook group is probably the easiest way to interact with everybody. You can post a photo or write something, and I'll keep the Q&A happening on the Facebook group. All right. Without further ado, let's go back to the lesson. So a little bit about me. If you have been onto our website, you would have heard a little bit about me. I'm the co-founder of Pinnacle Coaching College. We pretty much started with maths, and I am the head teacher for mathematics, so I pretty much responsible for our entire mathematics curriculum from year 9 all the way to year 12. I personally teach both extension 2 and extension 1 mathematics in the college, and you can trust that I have plenty of experience in this area. And you can see that last year, over 70% of my students achieved Band 6. So I know what I'm doing, and hopefully I'm able to share that knowledge with you. All right, so let's get straight to it. Now, this is in that booklet, that student booklet on our website that you can download. You don't have to write down everything. And this live stream will be uploaded as well at the end of this. So if you feel like you missed something, or I'm going too quickly, don't panic. It will be uploaded, so you can go back and catch up, and you can rewatch it multiple times if you want to. All right, so with these maximization and minimization questions, there's a couple of key steps you will need to follow. And to be honest, in any exam question situation, the question steps it out for you, and it takes you through the different sort of things you should do to get to the answer. I'll say, broadly speaking, it's probably divided into 3-4 steps. So the first step is you need to define what is the variable in the problem and create an expression for the thing you wish to maximize and minimize. So by thing, I mean it can range from volume, area, it can be a cost function, time function. It can be anything, really. You just kind of have to roll with the question. It is a problem-solving question at the end of the day, and sort of determine, okay, what's driving that sort of that particular object or volume or area or whatever it is, and then you create an expression for that. And basically, the next step is the actual maximization and minimization process. So I will say, broadly speaking, involves 2 steps. So you've got the first derivative, you have to solve it to 0. And once you've done that, you test the nature of these stationary points. So just like curve sketching, we need to demonstrate whether this is a maximum, minimum, what is it? Okay, so that's the nature. Now, you've got 2 options here, as we mentioned last week. You've got the option of the second derivative test, or you've got the first derivative table. I'll say, generally speaking, if it's quite easy to differentiate again to get to the second derivative test, just use it, because that's fast, right? You just sub a number in, you're able to tell. Otherwise, sometimes when the equation is a little bit extreme, it's very hard to do a second derivative, then you do a first derivative table. I'll give you a bit of tips and tricks around these as well when we get to it. And most importantly, answer the question. I've seen so many students who basically completed step 2 is like, yay, I got it to be maximum or minimum, but haven't addressed the question. So read the question. Sometimes it's after the maximum area, for example, or sometimes it's just after the dimensions that maximizes the area, and so on. So make sure you address the question. And that's true for any exam question. I keep reinforcing this point with my students, and I hope this sticks with you as well. All right, so moving on. A little bit of a pro tip here. Now, the steps I've just summarized for you pretty much applies to 90% of the question in this area. Yeah. So, I mean, we're using calculus to identify the minimum or maximum point, but to be perfectly correct, that's not really the entire process, although 90% of the question pretty much stops there. You just look at the maximum or minimum turning point, and that's most likely your answer. But it's important that you know we are looking for, let me just use a different color. This is already right. We are looking for the global maximum and minimum. Global means, so let me just draw a graph for you to demonstrate this point. So let's say I have a graph here. Just circle a couple of points. Okay. So the derivative process only gets you turning points like these guys, right? But they're not necessarily the highest or the lowest point in the given domain. So the terminology here, for example, this one, it's a local maximum. This one, it's a local minimum. And this one here would be considered a global maximum. And this one here would be considered to be a global minimum. Okay, so that's kind of my point here. Your highest point is not necessarily on the turning point. It can happen at the endpoints of the domain. And that's pretty much the 10%. The hardest type of questions in this area will be looking at values at the endpoints of the domain. Okay, so I just want to highlight that, especially for those students who are really aiming for band 6, you have to be aware of these little tricks, yeah, so you don't fall into the traps they've set up for you in the exam. Usually, I would say there are very obvious restrictions in a lot of these problems. So, for example, you're working with lengths a lot of the time, so lengths can be negative. So that would be one example. Okay. So we'll definitely take a look at a problem with this particular issue, and then we'll see how we'll deal with it in a moment. All right, so again, I just want to remind you guys, if you have any questions, or I'm going too quickly, or I'm not making perfect sense, let me just flick back to the page. Yeah, feel free to type in something to chat here. Yeah, so that I know, okay, I need to slow down, or I need to address any questions, or feel free to post something onto our discussion group. All right, so let's go back to the presentation. All right, so let's start with a baby one, very easy, simple one. We've got a rectangular box with a square space, no top. So as illustrated here with dimensions x, x, y. Now we're given that the volume is very much restricted. So quite often something like that gives you what I call something that links your variables together. Okay, so links your variables. Okay, your variables being your x and your y. Okay, so we'll look at that very shortly. Our first objective here is to show that the surface area is given by that expression there. Okay, so let's go straight into it. So let's start with, well, what exactly is the surface area? So the surface area, if you think about it, we've got 1, 2, 3, 4, and then the bottom side, 5. Okay, so the bottom side it's an x by x square, and then the four sides, it's an x by y rectangle. So we've got 1 of this and 4 of this. So the surface area will simply be 1 of this, so x squared, and 4 of this, so 4xy. That's our starting point. Now, just eyeballing this, you can see this is obviously not the same as what we're trying to deduce. What do? Well, looking at it, it looks like y has been replaced with something because there's no y in your final expression. So you need to find something that links x and y together, and that's that comment I made right at the beginning. Yeah, so that's going to give you your link. So we know that volume of a box like this will be x squared y. Yeah, so x times y. So this has to equal to 500 according to the information. That means if you make y the subject, y is equals to 500 on x squared. Easy, right? So now we put this back into here. And then simplify. So 4 times 500 is obviously your 2000. And then you have x on x squared, which gives you a single x on the bottom. And that's it. Done. Piece of cake. All right, so I'll say, just going back to the question here, you see how this exam question pretty much follows the structure I talked about right at the beginning. Usually the first subpart is about building the equation for the thing you want to maximize or minimize. And then the second part is the actual minimization or maximization, which is the calculus part. I'll say for a lot of students, that first part tends to be the more difficult part, trying to build that expression. The second part is more stock standard, just doing derivative. Unless the expression is very hard to differentiate, usually it's not an issue for most students. All right, so let's have a look how we do that second part. All right, so let me just copy the equation from the first part. So we have it in front of us. All right, so as mentioned before, we are going to use calculus to find the turning point. So what I'm going to do is just change the indices a little bit. Okay, and we're going to find the first derivative. So let's do that. So differentiate it. So dA dx. So bring the power down, subtract the power by 1. Same with that next one. Bring the power down, subtract the power by 1. Simplify. All right, so that's it. Now we need to solve it to 0. So I'll do it over here. Move that to the right side. Multiply that. Divide that. And then cube root 1000, which is 10. All right, so once you've identified the value that makes the derivative goes to 0, is that it? Not quite. You still need to, so there's 2 steps to this, right? One step is to find where the derivative goes to 0. And then the second step is then about showing this gives us the least area or the minimum area. And we do that by a second derivative or a first derivative table, depending on how easy it is to differentiate. So given this one's quite easy to differentiate, so let's just differentiate that again. So I'm just differentiating this thing essentially, okay? So let's see, minus 2000 times minus 2x minus 3. Okay, so that's not too bad. All right, so the point you're testing in there? Now at this stage, just looking at this is clearly positive. So that would be 4. 4 plus 2 is 6. 6 is a positive number. Remember what the second derivative means. So we went through this last week. If you've missed out, go check it out on our website. So second derivative is concavity. Positive means concave up. Concave up means you have a minimum turning point. So therefore, you've got a minimum at x is equal to 10. And that's it. Okay, so now that we've found the value for which the first derivative goes to 0 and show that it actually produces a minimum, we have to answer the question. Yeah, don't just stop there. Answer the question. It says find the least area. So we're finding the area. Now I'm going to use a different color and try to squeeze it here so it's less confusing. All right, so therefore, the minimum area is equal to, you just sub 10 back into it. All right, so putting that into the calculator should get you 300 centimeters square. And that is it. Okay, so to summarize, let's summarize what we've done so far so we don't get lost along the way. So the first step is trying to build the formula. So the formula is, well, what we're building is the surface area of the box. So we start with just building out, well, what it's meant to be in terms of the variables. So you've got x squared and 4 of these, so the 4 sides to the box, 4xy. And we use the fact that volume is restricted to 500. We got an expression for y, put that back in, we got the area. Second step, find the minimum area. So we take the expression, found the first derivative, solve it to 0, found that x is equals to 10. Then we establish that it's actually a minimum by putting it into the second derivative, which proves to be a minimum. Once we found the minimum, we address the question, find the least area. So the least area is meant to be sub 10 into here, which is basically this blue part, 300 centimeters square. And that is it. So that's a basic introduction type of question, just to get us warmed up and be ready to tackle some of the harder questions. All right, if you have any questions at all, I would like to remind you, don't forget there is a chat box next to the live stream. Yeah, feel free to write your comments there. Moving on. So the second question, I've selected this one. So the first one, I think, is a very basic volume / area linkage. This is a more of it's also sort of playing with volume and area, but it has a little bit of an extra similarity component attached to it, which makes it a little bit more challenging. And this type of cylinder in a cone situation is very, very commonly examined in most assessments. I see it come up so many times in any given year. So it's good to know how these guys operate. All right, so let's understand what's going on in this question first. So we've got a cylinder of radius r, height h, so you can see that in the diagram. So h is just referring from there to there. Inscribed in a cone of those dimensions, radius 6, height of 20. We want to show that the volume is given by that. All right, so let's do that first. Okay, so before we dive in, let's quickly revise how do you calculate the volume of a cylinder. The volume of a cylinder is equals to area times height. So pi r square h. So with that in mind, just an eyeball comparison, pi r square h, that does not look like what we have in the question, but that gives you a big clue around what you're trying to do because there is no h in there. So you need to link h and r together. All right, so this is where you need to do some analysis. All right, so imagine if you cut this up, okay, what you will get is something like this. Something like that. Okay, so I'm just going to write in the dimensions. So that's meant to be h, that's meant to be r, and the bigger one is that one here, which is 6, and this one is 20. Okay, so also doing some basic maths. This is 20, this is h, so this would be 20 minus h, and this bit here will be 6 minus r. Now, let me also label that. Oops, that's meant to be r, that's meant to be h. Now, what a lot of students miss is that there's actually 3 sets of triangles that's similar here. You don't need to prove similarity if you're just trying to apply calculus to this, so this type of calculus question, unless they say prove similarity, you don't really need to do it. There are 3 sets of similar triangles, so 3 similar triangles. Okay, so let me just show you, because these are all right angles, mind you. Yeah, because that's essentially a rectangle. So one here, one there. Let me draw it out. And then there is a big one. Yes, the big one on its own is part of this similarity family. Okay, so let's call them 1. Actually, yeah, A, B, C. That's confusing. A, B, C. Okay. All right, so this is where you then compare which one's going to produce the result you want. And you'll get very good at this once you get closer to the HSC and hopefully before trials as well. It's how to use the question to give you hints as to what to do. Yeah, don't just go off a tangent independently without regard to the question. I see that all the time. Always look at the question first and kind of deduce where you're supposed to go from there. And what that sort of does for you as well is, firstly, you don't waste time doing unnecessary steps and start going in circles and realize, oh, hold on, I wasn't even meant to do that, right? And the second step, the second advantage of sort of checking what you're trying to do is to make sure you are addressing the question. All right, so let's have a look. It's meant to have a 6 minus r in there. That will be the key thing I noticed in the question. So which of my triangles have a 6 minus r in there? Well, A, right? So you can see the 6 minus r in there. So I will definitely use A. And usually in these cases, I will usually use the big one as well, C, because it's all numbers. It makes it very easy to work with. All right, so using similar triangles, A and C. So H on 20 is equal to 6 minus r on 6. Or you can write it in whatever way you want. So the sides are in the same ratio, essentially. So h on 20 is equal to 6 minus r on 6. Okay, corresponding sides of similar triangles are in the same ratio. Times the 20 across. Now, if you picked up the wrong triangles, does that mean you won't get there? No, not necessarily. You will probably still get there with a bit of algebra rearrangement. It's just not the quickest way there. And in an exam, time is precious. So unless you want to start going in circles, I will just go with the easiest approach. Okay, so I'll just simplify the 20 on 6 into 10 on 3. So now we've got the H, come back to the volume formula for our cylinder. So the volume is meant to be pi r square h, which we've just deduced the expression for. And then you can see that's matching already. So now I'm just going to copy the question so it looks exactly like what is in the question. Now, this is a little tip from me as well. You'll hear me mention this a lot in these videos because sometimes when you're in the middle of the exam, you don't think about these things. You just want to focus on answering the question. But at the same time, you're also wanting to maximize your marks in the exam. So there are little tips I can sort of share with you how to do that. And the one thing, especially with these proof type of questions or show type of question, is if you feel like, oh, I kind of know what I'm doing, I kind of know how to get there, and you feel like you're only 2 to 3 steps away, but you just can't get your result to look like the final result, copy the question into your final step. And I can tell you it has worked for many of my students. In fact, one of my students recently told me she used that trick in her prelim exams and she got the mark because the teacher couldn't see that, she kind of did have some disconnect between her working. She literally just copied what was in the final answer. She couldn't get it to work, right? But she copied in the final answer. The teacher didn't pick up. She got full marks. So that's something I would like to remind everybody. At the end of the day, the person marking your exam is a human being. They miss things. So you can use that to your advantage. Be strategic. All right, so next up, we want to then find the values of R and H such that the cylinder has the maximum volume. So let's start with the equation. Always start with the equation. So I'll start here. Now, depending on how strong you are with your derivative, you might want to just fully expand this and just differentiate like term by term. But I want to show you a very little, a very neat trick to keep the derivative quite clean and easy to work with. So just to sort of summarize what I'm going to do next, we are trying to maximize the volume, so we need to find the derivative. Now, 10 pi on 3, all constants. Constants don't really affect your derivative anyway, so you can just keep that in front, okay? So what I'm going to do is just focus on this part, okay, where the variables are. And I'm just going to expand that. Okay, this is why constants are not in your way. You're not getting confused by constants. Focus on differentiating the r's. All right, so let's do the first derivative. All right, so differentiating that. Yeah, you see I'm just completely ignoring the constant, just stays in front, doesn't affect my derivative. I'm just differentiating what's in the bracket. Cleaning that up a little bit. And now we're going to solve to 0. Now the advantage of leaving it factorized like this is makes it very easy to solve to 0 because constant is irrelevant when solving it to 0. You're just solving that to 0. I'm going to factorize that. So you can see R is 0 or 4. Now, don't forget what R is. R is the radius of the cylinder, so it probably shouldn't be 0. So since R is length, R should be greater than 0, so R is equals to 4 only. All right, is that sufficient? Absolutely not. You need to show me that's a maximum. So go and do the second derivative, or you do a first derivative table as well. That's fine. Okay. So I'm just going to differentiate that. So leaving the 10 pi on 3 in front and differentiating what's in the bracket. Simplify. I forget how much room these guys take. All right, so what we're doing, we are showing 4 gives us a maximum. So sub in 4. All right, so that should get us minus 12 in that bracket, which simplifies to minus 40 pi. Okay, key point being it's negative. So negative means concave down. So we have a maximum. R equals to 4. All right, so answer the question. Find the values of R and H so that we have a maximum volume. So H, just going back, H is equal to 10 on 3, 6 minus R. So let's find out what H is. Okay, so subbing in R, put that into the calculator. That should get you 20 on 3. All right, so that's it. So a good student will actually answer the question. So I'm not like hunting for your working or hunting for your answer in the working. So therefore, the maximum volume or the cylinder is maximized when H is 20 on 3 centimeters and R is 4 centimeters. That's it. You can even underline it. Okay, it just really helps. Sometimes students tend to forget it's a human being who's marking on the other end. So the easier you make the job, the more likely you're going to get the marks. So keep it clean, keep it simple, highlight the answer. I'll say those are the 3 things. Let's go back and summarize the approach to this question. All right, so the first step of this question was to build the equation. To build the equation here, the linkage between the variables, which is your H and R, came from similarity. So remember, there are 3 similar triangles in this diagram. So one here, another one here, and then another 3rd one there. So that's your ABC. Okay, then you check your question. You're meant to have a 6 minus R, so pick the triangles that's going to produce 6 minus R. So that would be this one for sure. And always use triangle C, which is the big one that has numbers in it. All right, then you equate the sides. So H on 20, it's the same as 6 minus R on 6, yeah? Sides are in the same ratio in similar triangles, and you'll get that relationship. Then you sub that into the equation of a cylinder, and you'll get to the answer. Nice and easy. The second part, very stock standard type of derivative. So what I've done is you take out the constant first, and then I focus on the R component, so expand it in there, and then just differentiate what's in the bracket. It just keeps things very clean and easy to solve. So you differentiate it, solve it to 0, you get 0 or 4. Couldn't be 0 because it's a length, so it has to be 4, but still establish that it's a maximum. So second derivative, sub it in, it turns out negative, consistent with the conclusion that it's a maximum. Answer the question, which is what is H and R? So R is 4, H is 20 on 3. All right, so these 2, I would say, still fairly simple. I mean, as long as you've seen how it works, usually it's not that hard. All right, so now let's move on to the next 2 questions. They are a tad harder. So the next one is an example where the answer might not be as straightforward as just looking at the turning point. There may be some stuff hidden in the endpoints of the domain. But let's not get ahead of ourselves. Let's have a look at the question first. All right, so what we have here is we've got an oil rig. So this is the oil rig, 3 kilometers offshore from a power station. So that's the power station. All right, so we're trying to join P and S together somehow. Now there's a couple of ways you can do it. You can either go super long way. So cable all the way across the shore and then all the way across the sea. Yeah, so 5, 3, yeah, to get to west. Or you can go directly there, so straight there. Or there are some intermediate solutions. So we can do partway shore and then partway sea, or etc, etc. So this is a very classic type of maximization, minimization problem. So there are two extremes. So 1, 2 are both extreme cases and everything else is in between. And that's sort of also hinting at the fact that those are the endpoints of the domain. Those extreme cases, yeah, it's probably where the endpoints are going to be. So we'll come back to that. All right, so to do the shoreline, it's only going to cost us $1,000 per kilometer. And to lay the cable underwater, it's a little bit more expensive, $2,600. So R is the point closer to shore, okay, so you can see all of that, and that's just telling you all the information, okay? So let me just note this down so we don't forget. So that's $1,000 to lay the cable here, and then $2,600 to lay the cable here. All right, so in the first instance, we want to find the total cost of laying the cable in a straight line from P to R and then R to S. So we are looking at one of the extreme cases. Bam, bam. Very easy. I mean, if you can multiply and add, that's pretty much it. So $1,000 times 5 kilometers. So that's to the cost of laying the cable here. And then $2,600 times 3 kilometers. Okay, so that's the cost of laying the cable there. Put that into the calculator. It should cost you a total of $12,800. That's it. Nice and easy. Moving on. Next part. Find the cost of the laying the cable in a straight line from P to S. So this time we are going straight there. So to go straight there, firstly, this is entirely underwater, so it's going to cost you $2,600 per kilometer. And we need to work out the length first. So using Pythagoras, that turns out to be root 34. Okay, so that's root 34. All right, so therefore the cost of laying the cable from P to S will simply be 2,600 times the length. All right, so let's work out what that is. Oh, no, I got it here. Hold on. All right, so that is it. Nice and easy. So these are giveaway marks if this appears in the exam. They are just very, very basic parts, just getting you to explore the extreme options. All right, so now let's go on to the fun part. Part 3, let's see, be the cost of laying a cable from P to Q. So we're looking at all the intermediate situations. So from P to Q and then from Q to S, and we want to show that's the cost. All right, so just in terms of working out the lengths, we've got this is 5 kilometers. This is X, so that must be 5 minus X. And this bit here, it's a right angle triangle, so using a bit of Pythagoras, that will be 9 plus X squared. So in other words, now don't forget what was the costing, right? If you're doing it on the shore, it's $1,000. If you're doing underwater, it's $2,600. All right, so let's build that. So the cost will be the cost of cabling from P to Q, which is $1,000 times the length of cable required, so 1,000 times 5 minus X. And then we've got from Q to S. So plus 2,600 times 9 plus x squared. Then we just have to make this look like what's in the question. So take out 1,000 first. So that's 1. And that's 2.6. And now it's about making that look exactly like what's in the question, because that's pretty much it. So just tidying it up. Now the reason why I do that, I mean, this step is pretty much it, right? Why do I bother to write an extra line to make sure it match? It just goes back to human nature. You know, when I mark something, right? I look at it, I compare it to the answer. That's the first thing. If it looks different, it makes me pause and then investigate, is that the same thing? Now, that's the last thing you want a marker to do. You don't want them to pause. You want them to go, oh, yeah, that's the same, tick, 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 tick. Yeah, and you hope they miss any mistakes. That's what you want. So if you want that, make it look exactly the same as the question. And that's it. Nice and easy to build. That's not a difficult build at all. This is a difficult differentiation though, so let's look at the next part. Find the minimum cost. All right, so let me just copy the cost equation first. All right, so that's it. And I'm just going to do one more thing to it. I'm going to change that to the power of a half to keep things simple. Okay, so now the differentiation. This equation is actually very similar to the other one we did, like just keeping the constant in front. And that's kind of what you want to do here as well. Just keep the constant in front so that it's not kind of in the way and you're really just differentiating what's in the bracket. So let's do this. So differentiating 5 is 0 minus x minus 1. Differentiating this chain rule, so bring the power down. Subtract the power by 1. Multiply by the derivative of the inside. And now we simplify. So that's going to cancel. So you have 2.6x. And that thing is 1 over square root of that. Now, if you're not changing things from indices form back to the, I guess, square root form, I know a lot of students do that. They just keep the answer in indices form and then struggle to do this part. All right, so start making a habit. Yeah, don't let indices law be where you fail, right? It's meant to be something easy anyway. So just go and practice. Don't be afraid. Don't leave ugly indices. So negative indices or fractional indices. As is, practice changing it back, because that's going to help you immensely later on in this course. All right, so what do I do with this? Solve it to 0. Okay, so pretty much you're solving that to 0. And what I'm going to do, might as well just move the 1 to the other side. So it's plus 1. Multiply that across. Square both sides. That gets rid of the square root. So 2.6 squared is 6.76. Make x squared the subject, so move that to this side. So that's 5.76. Divide the 9. So 9 over 5.76 is equal to 25 on 16. What such nice numbers. All right, so the square root that's plus or minus 5 on 4. Now, because x is a length, it shouldn't be negative, so it automatically reject that negative answer. So let me just continue here since x is a length. Therefore, x should be positive, so therefore x is equals to 5 on 4 only. All right, I think I need a new page. Let's see if I can do this. All right, that worked. Good. So we've found the value. We're not done yet because we still need to show that it's a minimum. So moving on, testing. So let's copy the derivative across first. Now, usually, well, the previous two questions, I've done it using the second derivative. I'm not keen on differentiating that. I don't know about you. So I'm doing a first derivative table. So here we go. So 5 on 4 is 1.2, I think. Yeah, 1.25. All right, so you can pick a number lower than that, and above that maybe 1 and 1.5. I think these are good candidates. So all you're really doing is sub 1 into wherever you see x. So to speed things up, I've already done that. So minus 177.8. And if you sub 1.5 in there, that's 162.7. Number is irrelevant, it's the sign. So negative is sloping down, stationary, sloping up. That means minimum. Now, it's a little bit of a tip from me. I mean, depending on your school, this may or may not work, but this definitely works in the HSC, is this. So let's say you got to here, you're like, oh my God, I'm running out of time. I don't have time to sub in like numbers into such a complicated equation. You go with the fact that you know this is going to be a minimum. So you kind of reverse engineer the table. So it will look something like this. So you know you're testing 1.25, you know that's 0 because that's where you got it from. And then just pick some numbers above and below the point you're testing. Now you know that's what you're shooting for. So that should be negative sloping. Just write in negative, and it should be positive sloping. Okay, so just write that in and go therefore is a minimum. If you have time, come back and fill in the numbers. So it has worked with varying success depending on the school. So some schools are actually pretty strict about this because obviously anyone can just reverse engineer the table. So some teachers have said, no, you have to write me the number. The sign is not sufficient. Even though you say, oh, I've done the testing, it's on my calculator, that might not be sufficient for some teachers. But from some other teachers, it's enough to just write in the sign. I'll say generally in the HSC, if you're desperate, just write in the sign. Otherwise, do the numbers properly. Just don't give anyone any excuses to take marks off you. All right, so once I've done that, let's go back and look at the question, make sure we've addressed the question. Okay, so we want to find the minimum cost. So we still need to find the cost. So let me sub this into the cost equation. Let me use red again. All right, so the cost equation was all right, so it was this. So sub 5 on 4 in there. Or 1.25. That might be easier for you to put into the calculator anyways. Okay, so putting that into the calculator, that should hopefully get you a magical number of $12,200. Okay. Answering the question, therefore, the minimum cost is $12,200. And that is it. Now we've addressed the question. Now, before we go on to the next part, let's just take a step back and see what the story has been so far. So going back to the prior parts, you see how in the first two parts we've calculated the extremes. So the one extreme is going super long way, short, and then straight across. That costs us $12,800. If you're feeling extra luxurious and want the cable all the way across directly underwater, that's going to cost you $15,160. So $15,000, $12,800. Then we compare to the minimum cost, $12,200. So you can see that that is the lowest cost, even after having regard to the two extreme cases, which is good. Yeah. So use this type of logic check to make sure your answer makes sense. All right. So moving on. The fifth part. So we've got some sort of new technology, and that means the cost of laying the cable underwater can be reduced down to 1,100 per kilometer. Okay, it looks like I'm missing a question here. One sec. Oh no, the question is the next part. Okay, so the question is actually that. Accidentally split it up by accident. All right, so we want to determine the path for laying the cable in order to minimize the cost in this case. So coming back here, let's analyze this. So the shore cabling cost is still $1,000, and the underwater cabling cost is now $1,100. Now going back to the cost equation. So what would be the part that this affects? Well, $1,100 is now the new underwater cost, and the previous one was $2,600. That's where it came from. So, I mean, don't need to rebuild everything. Just replace that with 1.1, right? That's the effect of this. So just also going back to copy in the derivative, right? I'm not redoing the derivative. I'm just copying it. So that was the original derivative. So same idea. Just replace the 2.6 with 1.1 and that will do the job. All right. So what we're going to do is kind of redo that dc dx is equal to 0 component and see if we can get a new value. And let's see if it also makes sense as well. Let's have a look. All right, so we're solving this to 0. So moving the -1 across should be +1, and then square, multiply across, square everything. So 1.1 squared should be 1.21. Solving for x. So square root that, 9 on 0.21. It's not going to be a nice number, so it's about 6.55. All right, so same idea, since x should be positive, x is only 6.55. In any case, 6.55 does not make sense. Can you figure out why? So the answer is here. X is talking about that distance there. If that is 6.55, it's even longer. So it's like here, right? For to minimize the cost, it's gone outside the sort of acceptable domain for this particular question. And that's a very clear hint that the answer is not going to be at that point. So let's note that down. So what does that mean? Now we go and investigate the two extreme cases like what we did at the beginning. So we are going to look at going from PR to RS and then straight directly there. So I'll do it in blue. So the first case, PR plus RS. So that's going to be nice and easy. So just 1,000 times 5. And then 1100 times 3. So let's see what that gives us. That should give us 8,300. Second case. So that was the first case, like that, and then like that. Second case, straight, directly there. Now, before, I think we already worked out this is root 34. So PS will cost us 1,100 times root 34. So just working that out, that should give us $6,414.05. Clearly, that's the lowest one, and that's pretty much your answer. Okay, and I think that's why this part is tricky. Yeah, you have to go and investigate the endpoints to figure out what the true answer is. So just going back to answer the questions, the questions on the next slide. So the path, so the question is, what is the path for laying the cable in order to minimize the cost? So therefore, the cable should be laid directly from P to S to minimize the cost. That's it. Yeah, and we actually worked out that cost is 6,414. And that is it. Not that tricky if you're out hunting for it. I can see that in exam conditions there might be students who get tricked by it, but apart from that, nothing too hard here. All right, finally, let's take a look at the last question, which is another example where we're playing with coordinate geometry number plane here. So there's a couple of errors I just want to point out here. So that A wasn't meant to be there. So let's get rid of that. And that dash wasn't meant to be there. Let's get rid of that. So I find that maximization and minimization questions involving the coordinate geometry number plane tend to trip up a lot of students. Just can't visualize what to do with the information. So what I'm going to do is just show you this as an example so we can see how this will work out. Let's read the question first. So we've got a stock standard parabola. We've got a generic point on the parabola. And we've got a tangent to the parabola that's going to intersect with the x and y axes. And we want to show that the tangent is given by that. So the first part is nothing fancy. It's just literally finding the equation of the tangent. So let's do this together. All right. So I'm going to go in and label the coordinate first. So don't forget that this is meant to be t minus b squared. If you haven't figured out where that came from, it's just when x is t, you sub that in, you get the y coordinate. All right, so standard steps for finding the tangent. First step, y dash. So y is equal to x minus b squared. Y dash, chain rule. So it's just 2x minus b. Second step, find the gradient of the tangent at the point you're looking at. And the point we're looking at is t. So therefore, the gradient of the tangent according to our y dash should be just t minus b with a times 2. Then the third step, we put this into the point gradient formula. So subbing all of that in there. So the point is this point, the gradient is that. So y minus. All right, so that's a straight sub. Now, carefully check it and see what the heck are we shooting for here. You can see that we're trying to get it to look like this. So instead of expanding everything, be strategic. I'm just going to move that to the right side. So I'm going to continue up here. Okay, so you can see t minus b is a common factor, which is kind of what you want. Take it out. Okay, and then simplify that second bracket. Now you see how I'm always checking the question as I go, and that's absolutely what you should do. Otherwise, you're just blindly manipulating, and you waste a lot of time. I see students do that all the time, blindly manipulating algebra without any goal. It's going to eat up a lot of the time. All right, that's it. So once we've got that, the next part is find the coordinates of the point T in terms of B. That will maximize the area, so the ABO. So going back to the diagram, we are trying to calculate the area. Okay, so what you're going to do is actually find the x and y intercept first. So let's come back. I will just draw like a mini version. So we've got the equation of the tangent. We just deduced that literally minutes ago. And I think that was B and that was A. That's a right angle triangle, by the way. We're looking at the area. All right, so to do that, first we should find out what A and B is, which is the x and y intercept. So sub in x equals to 0, y is equals to that. You might want to expand this out. That cancels out. So b squared minus t squared. All right, so that point there is 0, b squared minus t squared. And then finding the x-intercept, you solve y to 0. And you can now appreciate the form that you've got it in. Because if you're solving, well, this is irrelevant anyways, we are solving this part to 0 because that's where the x is. So x is equal to t plus b on 2. Okay, so t plus b on 2, 0. All right, once we've got that, the area, so remember the core steps to maximization and minimization. You need to build an expression for the thing you want to maximize. So half base height for a triangle. So half, let's call that O, OA, OB. OA is that distance there, which is just the x coordinate. OB is that distance there, which is that coordinate. And then simplify. What I'm going to do is factorize that. These two are essentially the same thing. So what I'm going to do is combine them together as a square. All right, so this is not exactly the easiest thing to work with, but we'll then need to differentiate it and go through your typical steps for maximizing an area. So what I'm going to do is fully expand this so that it's easier for us to work with. And then expand it again. I think that's everything. I'm just gonna clean this up and collect any like terms. So you've got 2b squared minus 1b squared, so that's b squared. And then you've got bt squared minus 2bt squared, so minus bt squared minus t cubed. Okay, so let me continue that on the next page. So we've got you know what? It would have been a lot easier if I just expanded it at this point. But anywho, I've done that now. Just use that as a cross check. So minus t cubed and then minus t square b. Yep, just checking. B square t. Yep. And then minus bt square. Minus bt square. So that's doesn't look right. Let me clean that up. So let me just clean that up. So see, we've got b squared t. Yep, that's good. And then b squared times b cubed. Okay, no, that was good. So you see how I'm cross-checking? I always do this. In an exam, yeah, let's say you've done it one way, it's like, I could have done this another way, or you can think of another way. Yeah, cross-check, cross-check. Absolutely need to cross-check. Okay. So let's start with the equation. So let me double check that's right. B cubed, b squared t. Yep. Okay. All right. So then differentiate first with respect to t. Constant, ignore, stays in front. Now b is a constant here. So that's just 0. B square. And then differentiating the t square, so 2t. With that. So let's clean it up a hand. Alright, so that's more or less it. Now we do need to solve this to 0. So to factorize that, use whatever quadratic method you are used to doing. 1 minus plus. Okay. So we've got b is 3t, so t is b on 3, or b equals to minus t, or t is minus b. Since t itself, if you go back to the question, since t was meant to be, whenever you're like, oh, have I got extra answers? Go back to the question and check t was meant to be between 0 and b. So that means that's the only valid answer. So therefore, t is equal to b on 3 only. All right, so now that we've got the magic number, we still need to establish that it is going to be a maximum. I think this one is easy enough to do a second derivative, so let's quickly do the second derivative. So we differentiate this again. So that just goes to 0, b squared, and then minus 2b plus, sorry, not plus, minus. And then we've got t is b on 3. Sub it in. And then very quickly simplify that. So that's minus 2b, so minus 4. So that's minus b. And b is a positive number. Remember what it was. It was a constant, all right? So that's negative. Maximum at t is b on 3. Now let's go and make sure we've gone and addressed the question. Look. So the question was, find the coordinates of t in terms of b that will maximize the area. So t was supposed to be like this. Yeah, just taking it from the question. So we sub in the value we just worked out. Simplify that second one a little bit. So that would be, I think, 4b squared on 9. Double check. Yeah. Okay. So therefore, when t is b on 3, 4b squared on 9, the area is maximized. That's it. All right, so that is a very good example in terms of just showing you how to work some of the coordinate geometry stuff. I've seen also a question where it relies on distance formula and you're trying to minimize the distance. So just be aware you can also do that. I think there are some questions like that in the practice set, so make sure you go and check it out. All right, let's summarize. So in this question, we've got 2 steps. We are looking for the equation of the tangent first, and then we do the maximization. Now, this maximization is very, very heavy. Just one all-encompassing question, so you have to do quite a bit there. All right, so the first step is to get the tangent, nice and easy. Standard tangent steps. Step 1, find the derivative. Step 2, at that specific point, find the gradient. So sub x is equal to t into y dash. Then point gradient formula. So the point is there. Now, once you sub it in, pause, check what you're shooting for. You're supposed to shoot for that. So I move that to the other side, factorize t minus b out, and then that is it. Then we are trying to maximize the area. So this is the tangent, yeah, the area bound by the x and y intercept and the origin. So the first step would be to find the x and y intercept. So sub x equals 0, find y, sub y equals 0, solve for x. Then it's just half base times height. Then from here, I just expanded everything and collected the like terms. Actually, it would be a lot easier if you just expand it at this point, but doesn't matter, it's already done. Use that as a cross check. All right, so once you fully expanded everything, then you find the derivative. So differentiate everything here. B's are constants, so treat them like constants when you differentiate. Solve it to 0. Factorize, you find that t is b on 3 or t is minus b. Minus b is excluded because of the restriction on t coming from the question itself. So t is b on 3 only. Once you've done that, get the second derivative and sub that into the second derivative. So we established that's a negative number, so it's concave down. You've got a maximum. After you've done that, answer the question, find the coordinates of t. So sub that back in, put it in, you get t is that, and that's when the area is maximum. That is it. That wasn't too hard. So hopefully that was helpful. All right, so just finally concluding the session. So thank you for watching this live stream, or if you haven't watched the live, feel free to also catch up on it when you have a chance. Hopefully you found all the examples very helpful. As mentioned at the beginning, just going back to our website here. So our website, so you come to our website, you can go to resources, Pinnacle Live online lessons. Let's close this. Go to lesson 2. You can re-watch the video here. It will be uploaded shortly as soon as I end this live stream. And this is the student follow along booklet, so feel free to print it out and you can follow along the questions I go through in the video. And finally, there's a practice set that you can do on your own. I think it's a great sort of booster if you want to practice that just before your assessments. So hopefully you found everything we've gone through helpful today. And if you have any suggestions or questions, go to our Facebook discussion group. And we'll see you next week. Thank you for attending.